let's look at max flow again. Okay. Today you'll see how useful it is. Last time we worked quite hard to see how to solve this problem. Just let me recall this. In this problem, you have a graph G. You have a source node and sink node. You want to send flow from a source to sink, and basically the flow in and flow out on any node need to be conserved, and you need that the flow on any edge respect the capacity. Okay. Like formally, you have this, right? You want to find the flow such that it respects capacity. For every edge, the flow is at most the capacity. And you have flow conservation. Flow in and flow out are the same for every node except sink and source and sink. Okay. And you have scale symmetry just for notation convenience. And yeah, the value of the flow is the net flow out of the source or net flow into the sink. And we want to find maximum flow. Yeah. Okay. We also look at the concept of cut, ST, like a AB, which is a partition of vertex set. We say that it's a ST cut if S is in A and T is in B. Okay. And the value of the cut, C of AB, is the total capacity of edges on one direction from A to B. Yeah.
This is just a quick question about the cuts. I feel like all the cuts that we've seen are like planar cuts where you can kind of draw a line through. Does it have to be like that on the graph? Does that make sense?
Well, it's not really the case. Like when you have a graph, any graph, right? And you just as long as it's you can label any node 0 or 1.
Okay.
That just define the cut.
So it doesn't have to be like one line going through it.
No. Okay. Yeah. Yeah. But you can kind of define something. But yeah, it don't need to be one line. But when we draw it, we need to draw it like this. Yeah. As long as the cut contains S and not contains the set A contains S and not T, then it's a ST cut.
So wait, does A have to be a connected component?
No.
Of the graph? Okay.
No. Yeah. Also, you can prove that the X is the connected S mean ST cut. But yeah, right now the concept of ST cut is just really any set containing S, not T. A contains S and not T. Yeah. Okay. And you see last time that mean ST cut and max ST flow have the same value. That's max flow mean cut theorem. One thing that I want to note is that here the capacity are always not negative. Okay. So the mean cut here is the one where the capacity is not negative. So if you allow the capacity or the weight of edges to be negative, then mean cut would be can reduce to max cut just by flipping negative and positive. But max cut is NP hard. David mentioned this last time, and I want to mention this to you. So what we talk about today is non-negative capacity. Okay. Also, if the capacity are integral, then we know how to compute integral max flow. Okay. Given max flow, we can compute mean cut. We see this too. All right. So now let's try to solve so many problems from max flow. Okay. The first problem is this. Minimum edge cut. So it's almost like mean cut basically, but let me ask you. You have directed graph, you have node S and T, and now there is kind of no capacity from the description of the problem, and I just asked for what is the minimum set of edges such that you can delete, once you delete E prime here, then S cannot reach T, right? For example, if I delete these 3 edges, then there is no path from S to T. How can you solve this problem once you know how to solve max flow and min cut? Suggestion. Yeah, Rob?
I think if you set all the edge capacities to 1, then the bottleneck for the water is that's where the max or the min cut is. That's kind of like the same thing as this.
Yeah, it's really the same thing. That is, okay, the algorithm is first set the capacity of every edge to be 1. Okay. And then let's try to compute min cut in this graph. Okay. So max flow and compute min cut. Okay. Well, and once you get a min cut, then E prime is just an edge that cross the min cut AB. And that makes sense because once you set the capacity of every edge to be 1, here, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? Now the minimum cut is the cut such that the edge going out of a cut is minimized now because the capacity on each edge is 1. So the capacity of the cut is just a number of edges crossing the cut. Okay. So the min capacity cut is just the cut such that the edge crossing it is minimized. The number of edges crossing it is minimized. Make sense? Okay. What about this? Next problem, maximum edge disjoint path. So I have a graph G. I have node S and T. I want to compute a set of edge disjoint ST path. Like the blue path here is one path, another path here, and another path here. These paths don't share any edges. Okay. Any suggestion how to solve this again? Yeah, Blake?
Can you do maximum flow on the graph? And then once you find
The capacity is what? The capacity of each edge should be what?
1.
1. Mm-hmm.
Once you find one path, you just delete it and then run it again.
Right.
Like delete all the edges on that first path you found.
Yeah, good. That's the idea. Like again, set the capacity to be 1. Then compute max flow. Okay, compute integral max flow f in this graph. This flow is integral, so the value on any edge is going to be 0 or 1. Okay, so it's kind of, you say that either you pick this edge or not. Okay, so now now the flow might look like this thing, basically, like a union of these 3 paths. That might be like how your max flow look like. It doesn't give you the set of paths yet. Okay, but the idea is that from this flow, you can actually really just decompose, like Blake said, decompose this flow into set of paths. How exactly? Well, I'm gonna tell you, and once you do that, then you return this set of paths. Okay, let me tell you a bit how to decompose flow into paths. Okay, suppose this is your flow, right? Now let's consider the drag that induced by the flow. What do I mean by here? I mean just forget like forget any edge outside the flow. Look at this flow. Okay. And like okay. That actually can be some. Right now in this picture there is no cycle, but actually it could be the case that it could be the case that I have some edge like this. Let's see. And then maybe like this. Some edge here. And then how do I create cycle? Like this maybe. And here. Okay. Then so you see that like if my flow looks like this, and then I have this guy too. Wait, sorry. And then I go this way, and I go here, and go here. Then at least there is a cycle, like a small cycle here. This is not a DAG yet, but so in general, like when you look at the graph induced by the edge of the flow, it might not be a DAG yet. But let's say that right now you have a DAG. Okay. Okay. This is like a DAG. There is no cycle. So what you can do is that you can just first like do DFS in this graph induced by the flow, starting from S. And if you do DFS from S, you know that no matter what, you will like end at T, because it just keep going forward to T. There's no way to come like back to any like every edge just keep going to like to sync. Yeah. So once you find this path, remove it from your graph. Right. Once you remove it, then I claim that after you're removing, the resulting graph is still ST flow. Why? Because there are two things to check about ST flow: capacity and conservation. Capacity is certified because you just remove things. So just reduce the flow value on some edge. But the flow conservation is also preserved, because look at this node, for example. It used to have 2 units of inflow and 2 units of outflow. But after removing a path, like the in and out degree is decreased by the same amount. Right? So for every node, you still have flow conservation. So after deleting, it's still it's just another ST flow with value decreased by 1. Make sense? So it means what? It means that you can repeat. Like you get the first flow, first path, and then you know that after removing the path, it's just another flow. So just find another path and maybe find this path. Okay. So you get a bunch of paths, and you know that all these paths must be edge disjoint. And the reason is that it's because you set the capacity of every edge to be 1. Right? So once you use some edge, you reduce the flow capacity, like the flow value on that edge from 1 to 0. It will not be used again. Okay. So my point is that when you have an ST flow, you can always find like disjoint path from S to T, how many? The value of the flow. Because when you start with a flow with value something 10, you can find one path and reduce the value of the flow by 1. So can you can repeat at least like 10 times. Yeah.
Is the flow necessarily going to give us a DAG, or do we need to take a step to get from the flow graph to get to a DAG?
Yeah, exact. Good question. That's the point that I mentioned in the beginning. Maybe you don't have a DAG in the beginning. You need to do something. Yeah. So, but suppose that you have a DAG. Do you agree now that from this DAG that have like is a flow with flow value V, you can extract V many paths that are the edge disjoint. Okay. So now, if the flow is not really a DAG, what do you do? For example, I just add this edge, maybe like this, and then this thing, and then this thing. Okay. So my claim is that what you can do is this. You can, okay, my claim is this. If you have a flow, F, right? But suppose that there exists a cycle, C, in the flow, like this one is a cycle. If you subtract C from F, that is, I just remove the flow on both edges here. Okay. Then this is still ST flow with same value. Why is that? Like, you need to check two things, right? Capacity and conservation. And capacity constraint is clear. You remove things. Capacity is even more respected. How about conservation? Well, like when you remove a cycle, like let's say that this is like some flow, okay? But if you remove a cycle, C from the flow, a cycle is a subgraph such that the in and out degree of every cycle is a subgraph that in and out degree of every node is the same. So when you remove a cycle, then the in and out degree of every node, like total in degree and total out degree of every node is decreased by the same amount if you remove a cycle. Make sense? Like when you remove a cycle from a flow, it's still a ST flow. Also, I claim that it's a ST flow with the same value. Why is that? Well, because the value of the flow is just total net flow going out of S, right?
Yeah.
If you remove a cycle, the net flow out of S is the same. If the cycle don't intersect S at all, that's clear. But even if the cycle intersect S, let's say like I have this cycle. And I remove this cycle, then like the total inflow and total outflow decrease at the same rate too. So the net flow out of S is the same. Okay. So the point then is that when you have like a flow, once you identify the cycle, remove it. It's the same, like it's still a flow with like a same quality. So it means that if you just try to do this thing, right? Do DFS, but when you do DFS and you identify some cycle, remove that cycle and continue. Make sense? Yeah.
And that trick of like removing a cycle, is that only useful for this problem when we want individual paths or?
Yeah.
Okay, only for this one.
Yeah. Yeah. Like if the flow itself have a cycle and that flow is a max flow, even if it has a cycle, it's a max flow too. Yeah. Okay. Good. Are we good about this? Okay. All right. So next is about this kind of similar problem, but how about unrelated graph? Okay. So here I have unrelated graph, S and T. Now I want to find like a set of disjoint paths. Again, H disjoint paths. But this is like undirected. Like in this picture, there are 4 H disjoint paths that are undirected. How can we solve this? The idea is, well, for any edge that are undirected edge, just how about just create like a 2 edges in both directions? A natural thing to do. And then set the capacity of every edge to be 1. Like, so you replace this undirected edge with like a basically 2 edge here, right? 2 edge, and set the capacity of each of this to be 1. And then you compute max flow in this graph G prime. Okay. Okay. Suppose that you get the flow and somehow like suppose that somehow if your flow somehow use this edge in both directions, what can you do? It's okay to remove them. Why is that? I claim that if the flow is such that it uses both edge, then that's just a cycle inside the flow.
Yeah.
And we see that we can remove cycle out of the flow. It's still the flow with the same value. Okay. So, yeah, if the flow use like the edge in both directions, can just set both of them to be 0. It's still the valid flow with the same value. Okay. But once you do this, it means what? It means that every undirected edge, if you look back in your undirected graph, every undirected edge will be used at most once now. It's either used in one direction or another direction. Okay. So you get basically now an ST flow such that every undirected edge is used, like it's going through only once. And now it means what? It means that you can just extract the set of paths from this. So you extract this path. It's going to be disjoint path because every edge is used by the flow only once and in one direction at most. And this set of paths will be maximum because like it comes from maximum flow. Yeah.
Basically, we're just doing the same thing we did before after transforming the graph.
Yeah. Yeah. Just transforming the graph into bidirect, like make each edge bidirectional. That's it. How about this one? Minimum edge cut, but like now the graph is undirected. You want to find a set of edges E prime such that when you delete E prime, then S and T is not connected. Yeah.
It's just min cut and then edges across A to B.
Yeah, but how do you like? Maybe describe me the flow instance that you call max flow, like or min cut, because strictly speaking, we need to work in directed graph.
Oh, okay. Okay, well, I guess could you just do the same thing we did last time?
Yeah, just again, right? Like kind of make every edge directed by adding two direction.
Yeah, and only use once in one direction. Like if they're crossing, then you take it out, or
Say it again.
never mind.
Okay. Well, but yeah, it's a correct idea. Like, again, make every edge bidirectional, right? And compute minimum cut in this G prime. Well, a minimum cut in G prime, like strictly speaking, like when we compute min cut, we want to like it's a cut such that the total number of edges going out or total capacity going out of a cut is minimized. But here is such that whenever an edge, like if there is an edge that go into the cut, there is another edge that go out too. So it's really now just count the number of edges that cross the cut in both directions. Right. So like what I mean is that if you count the number of edges that go out of a cut, it's just the same as the number of undirected edge in the original graph. And so the cut that is minimized is just the will correspond to the minimum number of undirected edge that you can remove to disconnect S and T. Okay. Okay. Wait. One sec. So how about this one global min cut? Here I don't have S and T. I just have one graph. Okay. And I just say, okay, I just want to delete E prime such that G is not connected. It has more than one connected component. I just want to separate some pairs from each other. Okay. Do you have suggestion how to do this? Like by calling many max flow or maybe? Yeah.
I was going to say this would not be efficient, but you would call that previous algorithm on all pairs
Exactly.
nodes.
Exactly.
graph.
Good. Try, like you know that minimum cut must separate some pair, S and T. So it must be min ST cut for some pair ST cut. So just try all ST and compute min cut. Return the minimum one. So what that takes n square max flow calls. It works. Can you reduce this somehow to just n calls to max flow? Yeah.
Would it work to take only one node and compare it to all the other nodes, because that one node has to be in one that node is always going to be in one of the partitions, basically, across the edge split.
Yeah, exactly. So instead of try all pairs, fix one node and compute min cut from that node to everyone. Why does that work? Well, okay. First of all, like global min cut is like min AB cut for some pair AB. Okay. Maybe this is not the right argument actually, but the right argument is like, yeah, like for any node A, you know that it must be on one side of a mean global min cut for sure. Like global min cut must separate A from some pair, from some B. Okay, so if you fix A and you compute min ST cut, like min AB cut for all B, then like okay, fix A, and you know that global min cut must separate A somehow. Like it might look like this too, but in this case, it still separate A from some other node B. Okay. So if you compute global like min AB cut for A to every node, and once you loop through to this guy, then and compute AB min cut, then you will get like global min cut. Yeah.
So is it true that if we have, this might be like the exact same thing that you just said, if we have like the set of A nodes and the set of B nodes, if we change, and then like naturally there's some S and T, like if we change S to be another S in another node in A, it'll be this exact same cut.
Good, exactly. Like if this is a global min cut, there's a global min cut is here, and this is A, this is B. Choose any node here, as choose any node T here, and compute ST min cut. It will just review the global min cut. Yeah. Choose any pairs that are on the different side. Yeah. Okay. Okay. So okay. So now, so that just takes nmax flow calls. Actually, you can reduce it even further. Like there is a way to do just log nmax flow calls. I will not teach it in this class. It's actually cute and simple, and you can look at it, like, yeah. Like look at this video. It's really cool. It's really like simple. All right. So next is the next problem, vertex connectivity. It's kind of similar, but yeah. Oh. Okay. So what do I mean here? I mean like you have directed graph and two nodes S and T. So now let me like talk about concept of vertex cut. I said that V prime is a vertex ST cut. First of all, if V prime doesn't contain S and T, like think of V prime as like the guy that will once you remove, you separate S and T. So it doesn't contain S and T, and once you remove V prime, then S cannot reach T. That's like a vertex ST cut. Okay. And here I want to compute minimum vertex ST cut. For example, like in this graph, once I remove these two nodes, then S cannot reach T. This is like vertex ST cut, and it's a minimum one too. Yeah.
I'm not sure if this works in every case, but could you do, at least in this case, if you do the min edge cut and then just see which vertices those edges are cutting off, you can like compute the min vertex cut from that. Does that work generally, or?
It's not work in general. Reason is this. So if you compute min edge cut, well, it will kind of return you, maybe use different. It will return you this edge, and this edge. Okay, this is okay. In this problem, it works, but let's see.
Like if you had one node with a ton of edges that connects between them, and then many nodes with where like two nodes, or like many nodes with one edge across. Like it doesn't take into account like their degree.
Yeah, let me try. Okay, I can see the example now. Good. So how about this? Like this is S, this is T, and maybe like you have you know that the mean and like this is actually okay. So this is one node here, okay. So it's going to be the case that I said this is like a really well connected here. This is very well connected here. In this graph, the mean edge cut is going to be this two edge. But you could actually remove just one node here. Yeah. So yeah, like cannot really solve this problem just by calling min edge cut directly, but there is a way. Yeah. How do you do this? So here is a trick, like that is quite nice. The idea is that you're gonna create another graph G prime by kind of splitting every node into two nodes. Just look at every node U, kind of split it, make it an edge basically. Split it into U in and U out. And then I put capacity 1 between these two nodes. The edge, that original edge from U to X, I'm gonna connect from U out to X in. Like so every node is split, right? So X would have X in and X out. I connect from U out to X in. And C to U, I connect C out to U in. So I hope you understand the construction. But the idea is that now it's like this edge here really kind of correspond to a node. Okay? We kind of make a node to become an edge. And it has capacity 1 here. Now, let me ask you, like actually like it suffices to compute some ST cut in G prime, but which one we should do? Which one we should compute? It's like you have S in, S out. This is capacity 1. T in, T out. Capacity 1.
S out to T in. Like
Yeah, you say S out to T in.
yeah, like the inner side.
Mm-hmm.
Yeah. Because otherwise we'd count like
Yeah.
S itself and T itself.
Good. Well, any other suggestion? Who think this one? Who think this one? Who think this one? Okay. Who think this? Okay. Well, the answer is yeah. You're right. Yeah. Well, okay. Actually, if you choose anything else,
That's
you're gonna have like the value of the cut is gonna be just 1 actually. Why? Because if you choose S in, there's a way to disconnect S in from everyone else. Just cut this guy. If you talk about T out, just cut this guy. The only thing that makes sense is like a S out and T in.
Can you explain why you have infinity signs in that drawing there?
How to design this?
Or the infinite, like why are the capacities infinite?
You will you could make it one, but it's gonna be easier for explanation in next slide.
Okay.
Yeah. The idea is I really kind of want my cut to really cut this guy. Really want my cut to kind of go cut through a node, not through any edge.
Oh, okay.
Wouldn't you have to make them 0 then? Because doesn't infinite mean that there is no? Oh wait, sorry, it's Maxwell, not never mind.
Yeah, right. Yeah. So yeah, okay, good. So let me explain why this makes sense, right? Well, you have A B. Let's say that A prime B prime is a S out T in cut in G prime. Now you know that an edge that crosses this cut must be of the form that it kind of goes through some node, in and out node. It cannot go through any edge that cross from A prime to B prime cannot go like this, because this is infinite. Yeah. Okay. And so once you have this, now I can define V prime to be a set of node U that correspond to the edge crossing the cut, because the edge crossing the cut is of this form. So if it's U into U out, then I just put U into my V prime. And V prime then now correspond to a vertex ST cut. It's and the size is the same as the mean cut in G prime. Okay. So the idea is that any S out T in cut in G prime really correspond to a vertex ST cut in original graph. So now it means that just compute mean cut in G prime, then you get vertex ST cut in G. Okay. All right. Next problem. How about we want to compute disjoint path, but now vertex disjoint. Okay. We want to find maximum set of disjoint paths that are vertex disjoint. Okay. Suggestion? How do we solve this now? Yeah.
We do the same transformation where we turn vertexes into edges, and then we do the same infinite other edges, and then one on the new edges we made, and do Maxwell.
Yeah, exactly. It's the same idea, and now the same transformation. Instead of looking at ST cut, now we look at ST flow. That ST flow will correspond to vertex disjoint path. Okay. Same transformation. Compute the integral flow. Okay. And okay, suppose that I compute integral flow. Now some edge actually has capacity more than one, but they claim that in this flow, every edge will have the flow value either 0 or 1. This is clear. If it's an integral, this guy will have value 0 or 1. Why? How about this guy? Why this must be 0, 1 as well? Yeah. Because of conservation, it can only take 1 from U out, so it can be maximum 1. Exactly. It take from the flow is conserved here from U out. U out can receive 1 flow. So any guy can receive at most 1 flow here. the same here. Everyone here must be integral 0, 1 too, because the inflow from here need to go out of u in. Okay, so it means that you really get like a flow that looks like a 0, 1 flow. That is like for every edge, it's like either you pick it or not. Okay. But from here, like once you get like this flow that is 0, 1, we know how to extract disjoint path from it. It's going to be edge disjoint path in G prime. But I claim that this will, like, just by decomposing, we know how to decompose it, right? Get from F prime, decompose it into edge disjoint path P prime in G prime. This is edge disjoint path, but I claim that this corresponds to vertex disjoint path in G. Well, because it's kind of because you have this capacity, right? Like you can construct vertex disjoint path in G, just like for every path in this collection, we kind of contract the in and out node into one node. And P prime is just will be contracted into the set of paths P in G. And now you know that every node here will appear at most once throughout this whole collection of paths because, well, the capacity of this edge is 1. Okay. Make sense? Okay. So that what we show so far is basically like a proof really quickly, like the really famous theorem from almost 100 years ago now, but yeah, by Menger, but it's like really fundamental in combinatorics, which says that minimum size of edge, like min edge cut, is the same as number of edge disjoint path. We know how to compute both of them, one of them using min cut, one of them using max flow, but the values are the same, so they must be the same. The same for vertex connectivity. Minimum size vertex cut is the same as maximum number of vertex disjoint path. Okay. All right. It works in both directed or undirected graph. And yeah, it's just a simple thing that we can prove immediately once we know max flow min cut theorem. Okay. Questions? All right. Okay. By the way, we can talk about what max flow with vertex capacity as well. Like you have the directed graph, and now you have vertex capacity on each node. Okay. That is, we want to find ST flow such that the total inflow into S into U for every node U is at most capacity of that node. Well, how do you compute this? Just do the same kind of reduction, split a node. But like now, like the capacity here is the capacity of the node. And once you compute the flow in this graph, by contracting this node back, it will correspond to the flow that respect the vertex capacity. Okay. Let's look at next scenario. Yeah, like you're gonna see like lots of application like this throughout this class. Okay. Suppose that there are like a bunch of IA applicants, right? And there are like some IA positions, like two side IA applicants and IA positions. And each IA is qualified to some subset of positions. And okay, I want to find like the maximum size of matching from IA's applicants to the position. I want to match as many people as I can. How can I solve this? Well, this can be modeled as a graph problem, where like first of all, a matching is just a set of vertex disjoint edges. And it's like I have bipartite graph where one side is like IA applicants, another side is a set of positions. And I want to find a largest matching. That's the maximum matching problem. So like the graph can look like this. A matching is just, a set of edges. I match the applicants to a position. And these edges don't share vertices. This is a matching. This is the maximum, not maximum matching. This is the maximum one. The goal is to find maximum matching. Okay, so how can we solve this problem? Yeah.
Oh wait, actually I'm not sure anymore. What if you connected everyone to jobs they don't match with, and then you find the min cut?
What if you connect?
So then it would like minimize the number of. Actually, never mind.
That's an interesting idea, but I don't think it's what I have in mind. Yeah. Okay. Yeah.
What if all of the A's were connected to like some node S and all the B's were connected to some node T, and you found the maximum disjoint paths from S to T?
Yeah. Good. So, yeah, exactly. Like, you connect the source to all the applicants. The position are connected to sink, right? And I try to just put the capacity of every node here to be 1, because it's like every guy here can be matched only to one job. And this position accept only one person. So it's like every node here has capacity 1. Okay. And then we compute max flow in this graph. Okay. Yeah.
Would this be different than just setting every edge capacity to 1?
Would be fine too. Yeah. Like I can set the capacity of an edge to 1 too. Yeah. Okay. Set vertex capacity to 1 and compute integral max flow. All right. So the flow now really kind of, when you forget the flow out of S and into T, the edge here, right? They will be disjoint. Like the edge cannot share vertices. It's just correspond to matching. This one will correspond to like matching. Why? Because like a node can have only one edge, one flow going through it. So like you cannot have more than it's. I hope you see that the flow here corresponds to a matching. So like there is a correspondence between this flow and the matching. We want to find, so once you compute max flow, it gives you maximum matching. So we can solve it. So that's how you solve maximum matching in bipartite graph. If the graph is not bipartite, you cannot use it. You cannot just solve it using max flow. By the way, it's much more complicated. All right. And okay, we want to prove not just how to solve maximum matching, but let's prove some just combinatorics statement again, which is like a Hall theorem. So it says this: if you have bipartite graph, right, such that the number of nodes on the left side is n, the number of nodes on the right side is at least n, and let's say that this neighbor set of S is just like basically the neighbor, like any node that is adjacent to node in S, that's neighbor set. Hall's theorem says that there is a way to characterize if the graph has a perfect meshing by just saying that like a graph has a perfect meshing if for every set S on the left, the side of its neighbor is at least the side of itself. For example, like this one, this is a set on the left, the side of its neighbor is 1. So you cannot have perfect meshing here. But if this is true for every set, then we can, the theorem says that then it must have a perfect meshing. So let's try to prove this quickly by using Maxwell mean cut. Yeah.
Sorry, what is S?
S is a set of vertices.
So just any subset of vertices.
Any subset of vertices on the left.
Okay.
Yeah. If the neighbor of a set S is at least a set side of a set, then it has a perfect meshing. So one direction is clear. If there is some set S such that this is violated, there's no way to have a perfect meshing like here. You cannot match these two guys. But the another direction is interesting. Okay, let's prove this. Okay. I forget to say that perfect meshing just means everyone here is meshed. Okay, let's try to prove Hall's theorem. Okay, one direction is clear. I'm gonna skip this. What if the neighbor set is the size of the neighbor is at least the size of the set for every set S. Okay. Well, when this is the case, I'm gonna claim that like every vertex ST cut in this graph, like I'm gonna prove this by looking at like ST instance, like flow instance, which is here. And if I look at this flow instance, I claim that in this graph, the size of vertex ST cut is at least L. I guess I'm gonna prove this later. But if that's the case, then we know that there must exist L vertex disjoint path in this graph. And from L vertex disjoint path, we get, it means it just corresponds to perfect matching. So now I just need to prove why this is the case. Okay. We good? Not or something? Okay. So let's try to prove this. Why the ST vertex cut must be as big as the left side of the graph. Okay. So let's say that the cut is like C. Okay. So like C can look like I don't know, look like this and then this. Okay. Or C can look like this. It's just a cut that once you like, it's a set that doesn't have S and T, and once you remove it, then it disconnect S from T. Okay. And I'm just gonna say that, okay, this is some cut, like vertex cut C. Let's say CL is the guy in the cut on the left side. And U is the guy that is not uncut on the left side. Maybe like this. This is a cut on the left side. This is not cut. All right. So, but we know that if this is not cut, then the neighbor of this guy, the neighbor of UL must be cut. right? The neighbor of UL must be cut, because otherwise, then like there is a way to go from S to T. But now what do we know? We know that the cut size is just this one plus neighbor of UL, right? But what is the size of this guy? Well, it's at least the size of UL by this assumption. But what is the size of this guy? It's L, like everything in L. So any cut is outside at least L. Any vertex cut is outside at least L. Okay, so we're done. We proved our theorem. Okay, let's go next. Next problem. Circulation. Okay. So this is a new problem. It's a problem where you have a graph. You still have edge capacity. But here there is no like a special sort and sink. Okay. We kind of have instead vertex demand D that assign value on every node. Not like usually like normally you have sort and sink where like the sink has demand and the source has supply and you just want to send flow from source to sink. Now I have like every node can have some number demand. Okay. And what we want to find is this. We want to find a flow, assign flow to edges, still respect the capacity, but the net flow on every node V basically satisfy the demand. So like this is the net flow into V. If the demand is positive, you should have some total flow into that node. If the demand is negative, then it's like a supply guy. Like the demand, the total flow out of this should be. If the demand is negative 10, then the total flow out of that guy should be 10. Yeah.
Is it the same demand for all? Is it the same demand number for all the vertices or a different one?
Different.
Okay.
Every node has different number. Yeah. And actually, like if there is some guy with positive, then some guy must be negative to make this possible.
So is this basically just max flow without the conservation requirement?
Yeah. It's like normally for max flow, you have that. It's like every node here has demand 0, and you kind of want to do it such that kind of S has negative as much as possible, and T is like a positive as much as possible, and everyone here is 0. Every node has demand 0. But now, like, yeah, we just want to find flow such that, yeah, can we satisfy the demand on every node? Or find such a flow or say that it's just impossible. Okay. Like, if I want to say, like, so you should see that this is like more general than max flow in the sense that if I say that if I set the demand of everyone to be 0 and I ask if this can be minus F and this is F, then it's just to ask if max flow value is at least F or not. Then I can do binary search to find the maximum flow. You see, right, that this is just more general than max flow by doing some binary search. Okay. So if it's impossible to send this demand, then it means that max flow must be less than F. Okay. Anyway, this is the problem. Like, for example, here you have like this guy have negative demand 2, negative 4, and this is 3 and 3, and this is 0. Yeah. Okay. And one way to find this circulation is like this. The outflow of this guy is 2 because it get 1 and it like send out 3. So like it's like a supply of 2. And this guy is like a demand 3. Yeah. Okay. So that's the problem. Now, yeah, now the thing is that I claim again that you can solve this again using MaxFlow. Although from the statement itself, it looks like a more general problem. It's just you can solve it still using MaxFlow. Okay. Yeah. Okay. So let's try to solve this using flow like MaxFlow. Well, I'm just gonna look at the negative guy and positive guy. The negative guy is it's a supply. It acts like a source, right? And the positive one is act like a sink. It want to receive flow. Okay. So we basically want to create some flow problem that decide if and say that the flow value is at least something, then the answer is yes. And if not, then there is no circulation. What would be your guess? How to decide how to design the flow instant that capture this one?
So I think sorry, what's the name for the D again? What's it? The demand?
Yeah.
So I think the negative demand has to equal the positive demand.
Yeah.
And so you're looking for a max flow equal to, so here would be 6, right? Because that's like the negative demand and the positive demand.
Right.
Maybe it would be 12. No, I think it's 6.
Yeah, is a good, what you said, this value should be 6. Yeah, because it's this guy, everyone here need to send out, and it need to be 6. What about but to really create a flow problem, you have a source, one source and one sink. How do you model this?
Could the source be connected to all of the people that give, and the sink could be connected to all of the people that take?
Yeah, just connect all the source, create the super source, connect it to all the supply guys. And the demand guy just connect to super sink. Okay, let's just see the pro. Yeah, I create super source and super sink here, and the capacity here is 2. This used to be demand supply of 2, supply of 4. I just put the capacity of this edge to be 2 and 4 and 2. And the same here for a sink, right? And if now I can send 6 value of flow from the super source into super sink, we just get the circulation that we want. Because it means that if I can send 6 value of flow, it means really that I send out flow 4 here and 2 here fully. These are all saturated. So it's really this guy indeed send 4 units of flow and send 2 units of flow, and these guys receive as much as it wants. Okay. Okay. All right. Okay, so add a sink and check that the flow value is the same as sum of positive demand and sum of negative demand. If the max flow is actually less than 6 in this case, just means that you don't know how to actually certify the circulation.
So if the sum of the positive demands doesn't equal the sum of negative demands, then there isn't a circulation?
Exactly.
Okay.
Yeah. If like the total supply doesn't really match the total demand, there's no way to certify this anyway. Yeah. So you know that the total positive one and the total negative one must match. That's like easy condition to check first. Yeah. Okay. Let's look at this one. Circulation with demand, but also some lower bound. Okay. So here is a new problem where like you have lower bound on capacity. What do I mean here? I mean like this one. Each edge has two numbers, L and C. And I want to find circulation such that the flow value respect the capacity, but also need to send at least L. Like need to have flow value at least L. I have both upper and lower bound on each edge. Now I want to I ask, can we see if there exists a circulation that certifies this on every edge?
Can't you just duplicate, well, I guess, because you have to choose one or the other. I was gonna say like duplicate each edge to have 2 or 4, but then that might allow you to pick both. So you just make sure you can only pick one.
Duplication doesn't really kind of force to have flow on it, right? Here I kind of say that I need to have flow at least 2 somehow. Okay. But there is still a way to reduce this to circulation, and circulation actually reduced to max flow, so you can solve this with max flow again. Okay, so how? Suppose that you have this edge that has a lower bound 1. Okay. So just imagine that you just send flow from this guy to this guy. Let's just set the flow value here to be 1. Okay. It means that if you assume that like you put the flow value here to be just 1, just from the beginning, you don't care about anything, just certify the lower bound first. Okay. Then you don't have lower bound anymore. And the capacity is decreased to from 3 to 2 because you used up 1 unit already on this edge. But now I actually will set this demand here to be 1 and demand here to be -1. Why does that make sense? Because I cannot force myself to send flow here from U to V. So in order to to find some flow that certify that allow me to actually send from U to V, then I just say that okay, I just kind of say to some smart guy say that okay, just find some flow whatever you can such that this guy receives 1 unit of flow, and this guy I need to send out one unit of flow. And if some guy find such a flow for me, then now I can just really send flow from U to V. Make sense? I just say okay, start with an initial flow that I send from U to V just to certify the lower bound. Make the lower bound disappear. But that kind of induce some demand. And if I can satisfy such a demand, then it's good. Then I can just indeed like send the flow, the initial flow that I want from the beginning. Question about this? So the idea is then like for every edge with a lower bound, right? I just think like I just send flow with that low bound from the beginning, and that basically create a demand. Like you kind of demand L unit of flow, and we kind of need to like send like need to supply L unit of flow, so the demand is less by L. So I just set this thing. Okay, capacity is also like set to be smaller, and just do this for every edge with lower bound. Once you do this, every edge has no lower bound, and now it's just circulation problem. So let's see example. Like you have this one. Okay, you just remove all the lower bound, and that induce some demand. Okay, and like from the circulation problem, you can reduce to max flow. And then if the flow value is is the same as a sum of positive demand, then you know that it exists as circulation. Yeah. That's it. Question about this? Okay, you are too quiet now. So you need to say, is it okay or not? Okay, right. Okay. So last example. Okay. Baseball. Okay. So like let's say that here is like there is some tournament, right? And this is like a number of wins on each each team. Like Minnesota get this much, Detroit get this much, Chicago have this much, Cleveland have this much. Okay. And now like what is this? This is a kind of the remaining number of match between each team. Between Detroit and Cleveland, they still need to play like 4 more games. Between this one, Minnesota and Detroit need to play 1 more game. And what if I asked you, is there any chance for Cleveland to win, to be the first rank? Like now it has like the last rank. Is there any chance for them to win, to be the first rank? Okay. If you ask this, well, like the first thing is to assume that, okay, let's say Cleveland win everything that it can win. But even if it wins everything that it can win, it's still not clear that it can be the first rank because this guy still need to play. And like the number of wins on this guy might increase a bit too. Okay, so but like if I assume that Cleveland wins all the remaining match, then it increase number of wins of Cleveland to this. What to do next? Now it's like the number of wins is like kind of the supply. The unit of win need to be assigned to some of this guy. Like the number of wins here need to assign to Detroit or Minnesota, and so this takes many of wins into assigned to Chicago or Minnesota, and so on. But in order for Cleveland to be the first guy, you know that Detroit can win at most 3 times. Otherwise, Cleveland is not gonna be the first rank, because if it wins more than 3, then it's more than more than 41. So I put kind of the limit of number of wins on each node here. So you see, like, it's like you have supply of wins, and this guy is like have capacity that you shouldn't win more than something. This is like a sink capacity of this guy. So with this intuition, you basically can just create like this MaxFlow instance, saying that this is like a number of wins that you need to assign, like, and like from between Minnesota and Detroit, there is like one supply of win, 1 unit of win. It can assign to either Minnesota or Detroit. And Minnesota should win at most something. Detroit should win at most something. And you just ask, can you supply, like, can you send this, can you supply the wins here from the source so that every guys here, like, receive at most this number of wins. This is just MaxFlow problem. So you just ask, like, just ask if MaxFlow value is 8. Basically, that is, can you send all the wins, which is in total 8, right? And in this case, not the case because you find a min cut that of size less than 8. So Cleveland cannot win, cannot have no chance in this case. But yeah, so you see, okay, let me wrap up quick. Like you see so many applications in this class, and not just like a bunch of algorithmic problems, but not just that. It's just to prove some theorem, some structural like combinatorics. You can use MaxFlow min cut just to prove that. But next class is about linear program, which is like kind of next level of this. Like it's just some thing that allows you to solve many problems and at the same time prove many combinatorics as well. So that's next class on linear program. Yeah, see you.